steady states, I'm going to dissipate an amount of energy, and I can also derive the power from it. So this is typically what we worry about in terms of the battery dying due to steady state leakages and power. Okay. طب this is the steady state. يعني if standing still, no change, no switching in the inputs, this is the power. It is the power would be VDD times ID, and it will be the average of being in the state of low output or the state of high output. Okay, so the P will be P out low plus P out high over 2, unless if we tell you it is not balanced. Here in this case it is balanced. We have 50% of the time in this state, and another 50% of the time we are in the other steady state. If it is unbalanced, then we multiply it by the weighted. Let's say that the output is low 30% of the time, then we put that weight into our average. Instead of here we are reflecting 50% in each of the two states. Hello. Now, in addition to the steady state power, well, the inverter, when it changes the state, it has to switch. So the output has to change. We need to charge and discharge the output capacitance. And the output capacitance, for example, in an inverter can be due to the wires it is driving to other gates or other places in the circuit, and due to the MOSFET internal capacitance. Okay, so anytime I switch my input, my output is going to switch, but this means that here I am discharging a capacitor or I am charging a capacitor. Okay, so therefore the dynamic power dissipation should be calculated, and we will start by taking the example of the resistor-based inverter. Okay. For the resistor-based inverter, which really is this inverter here with the transistor, and this is Vn, okay, and then it is driving some capacitive load, including its own self-capacitance. When the input transitions from 1 to 0, when the input transitions from 1 to 0, the output is going to transition from 0 to 1. Okay, and for a 0 to 1 transition at the output, the resistor is responsible for this pull up, because when the input is 0, the NMOS device will be off. Okay, so we will end up with a resistor trying to pull up a capacitor that was initially at 0, and the output is going to transition from 0 to 1. In this case, or in this scenario, we have V init equal to 0, and V init equal to 0, and V final equal VDD at the capacitor node. So let us see what happens. When we charge a capacitor from 0 to VDD, you have learned before that the energy stored on the capacitor at the end will be half CVDD squared, and this is from some integration of the work function. So now we're going to look and see if at the end the capacitor will store half CVDD squared. We want to see how much energy was delivered by the supply, and the energy delivered by the supply can be expressed as the integral as VDD times the integral over time of IDD, or IVDD basically, of T dt. But the current that is flowing in VDD is really the current that is flowing in the capacitor, and we know that the current that is flowing in the capacitor is really dq by dt. Okay, so the integral of I dt is really the integral of dq by dt times dt, which is the integral of dq, which is really finally the charge that is stored in the capacitor. Why? Because the capacitor started with 0 charge and it ended up with a charge equal to what? What is V final here? What is V final on the capacitor? It's going to be equal to VDD لأنه الcapacitor is like a reservoir. I have an RC time constant now. Okay, this signal now, it's as if when the NMOS turned off. Actually, let me clear. The true circuit looks like this. I had a resistor that was connected always to VDD, and it was connected to the capacitor, and then I had the NMOS device with another resistor Ron that is connected to ground. Initially, my switch was on and this node was close to 0. We will assume that it was VOL. Now when the NMOS turned off, and we will assume that VOL is approximately 0, this section, the switch turned off, it opened, and so now I'm starting with a capacitor, okay, whose initial condition is approximately 0, and now it is connected to some supply voltage, which is VDD, and it's going, this is VDD, and it's going to start to charge. It's as if the switch here closed, but there is no real switch, and it's going to charge to V final, which is VDD. Okay, so therefore, the charge at the end of charging, okay, the capacitor will have V final equal VDD, and it will have a charge Q equal C times VDD. Okay, so the capacitor will end up, once this node charges fully, خلاص I reached then my steady state, the capacitor would have charged CVDD, and it will be, the V out will reach to VDD. So let us see. Therefore, the energy that is supplied by VDD is equal to integral of the power, which is integral of VDD times IDD. Okay, and VDD is a constant, we take it out. The integral of I, we said that this is the same current that is flowing during charging in the capacitor. Therefore, it is VDD times Q cap, but Q cap is CVDD, therefore the total energy is CVDD squared. And what we are showing here is that I am going to supply CVDD square, and I'm going to store half CVDD square on the capacitor. Okay, so the amount of energy that is lost during this cycle is half CVDD square. Okay, so I stored half and I lost half of this quantity. يعني راحت heat dissipation in the circuit. Okay, so let us see now what this means. So let me okay. So let us see what this means, and let us start. Be clear. Okay, so what we are saying here is that I had a cycle. If let us say that this is the inverter, okay, and let us say that the input is going to be high to low, and then low to high, and it's going to repeat. And if I want to include one cycle of the input, okay, let us say that I'm going to start here, okay, when the input fell to low, and that I am going to stop here. And to me, this is one cycle T. And in relation to this one cycle T, Let me just draw it again. In relation to this one cycle T at the input, the output is going to respond. So the output in this cycle T, I am going to see it switch from high to low, and then now when the input again switches from low, sorry, pardon me. When the input is low, the output is going to be high, and then when the input switches to high, the output is going to be low. So my output is going to switch in this response. فإذا in the first part of the cycle, when my input switches to low, okay, in this first part of the cycle, when my input switches to low, okay, my output is going to switch to high. Okay, this is my output is going to switch to high. And then in the second half of the cycle, when my input goes back high, okay, then my output is going to transition back to low. So my output is going to transition back to low. Type great. We saw now in this first one cycle of the input switching, what we have is that in the first half cycle, yani when the input went down to low here, up till here, and when the output is charged, okay, the amount of energy supplied by VDD كانت C VDD squared, okay, and the amount of energy lost in the circuit كانت half C VDD squared, and the amount of energy that was stored in the capacitor كانت half C VDD squared. So now what is going to happen, this is what we have seen here so far. يعني لما الانبوت نزل الاوتبوت علي, the energy supplied CVDD squared, the amount that was lost can't have, the amount that was stored can't have. Great. Now in the second half cycle, when the input is rising, when the input rises, okay, what is going to happen is that the output will drop. We are going to discharge the capacitor almost until where? Almost until 0 تقريبا, يعني VOL is very small. Okay, so we are going to lose the energy that is stored on the capacitor. So in the second half cycle, okay, we are going then here, all of this were for charging the capacitor. How can we charging the capacitor? Okay, هلا in the second half cycle we are going to discharge the capacitor, and so we are going to lose the stored energy in the cap. هلا نرجع نفرجيها. We lose the stored energy in the capacitor. يعني I am going to lose the second half CVDD squared. Okay, therefore in one full cycle T, okay, in one cycle I'm going to lose or dissipate energy equal to C VDD squared. Okay, فإذا supply gives me CVDD square. Half of it is lost when I'm charging the capacitor, and the other half is lost anytime I discharge the capacitor. Okay, so anytime I discharge the capacitor, I'm going to lose the other half. Okay, anybody has any question? So, let us now follow the slides and see what they say, and then think of it. Now, some of you may ask, well, what if my input is like this, and then my output rises here, my input rises again here, then it takes longer time, and then it rises here. What happens to the output هيدا الانبوت. The output will be low and then it will go high and then it will go low again and then it will go high again and then it will go low again. Now here the period is not exactly the same, but what matters is when we count the frequency or how many times it is charged. Why? Because every time it is charged, it has to be discharged for it to be charged again. Okay, so if I count the frequency of charging or the frequency of this switching, the switching frequency we call it, is what matters at the output. Okay? So the switching frequency at the output is what matters. لهيك نحن حنبلش period and then we'll talk about the switching frequency or the frequency. So let us now look at here. Here they're telling me that for the transition from 1 to 0, assuming that our pull down is small, okay, in relation to the our pull up, so we're gonna ignore our pull up. What's going to happen is that the capacitor will be discharged mainly through the CMOS transistor, and the energy that is stored on the capacitor at the beginning is half CVDD squared, and then therefore we are going to lose all of it because we are discharging the capacitor when the voltage is around 0. We will have no longer any charge or any energy stored. Okay, so for one charge discharge cycle, يعني إذا هيدا VC or V out, if VC or V out looks like this, I have one charge and then one discharge. For one charge discharge cycle, the total energy lost is equal to CVDD squared because it is really the sum of the two energies that were dissipated in the charging and in the discharging. Okay, so accordingly, what we end up saying is that therefore now the power dissipated in the circuit. Sorry في lag بالiPad عندي واللابتوب. So the power of dissipation in the circuit is going to be dependent on the frequency. Sorry, I lost the iPad connection. One second. So the power is going to be dependent on the frequency of switching, and therefore, if the frequency equals 1 over T, if the frequency equals 1 over T, the frequency of charging and discharging, the dynamic power dissipation is CVDD squared, which is the energy over the cycle. So it's equal to F times CVDD squared. And this equation is very, very important. Then we will tell you. Now, in an inverter, if the input is switching at some frequency F, then the output also will switch at the same frequency, right? So the output will switch at the same frequency F. Later, when we take a little bit more complex gate like the NOR or the NAND, we will see that the frequency depends on the two inputs. So what we care always for is the frequency of the output, because it is really the frequency at which the capacitor is charging or discharging. Okay. Anybody has any questions about the dynamic power? Okay, so just like there is dynamic power and we need to charge and discharge capacitor, this means that anytime I have a C, I have an effective RC time constant, and therefore I have a delay. Okay, so I will have a delay. Now, if I have a delay, typically for our purposes, we are going to assume that the input is switching instantaneously. So the input has already assumed its a new state, and really we measure the delay as the time it takes the output to switch to its not steady state but 50% value. يعني if my input is going up high, then I expect the output to go from high to low. لأنه steady state بده يصير low, بس it is going to go from high to low, and I'm going to measure what we call TP high to low. So when we tell you measure the TP high to low at the output, this means that the output is transitioning from high to low. Okay? Typically, the TP high to low is really T2 minus T1, where at time point T1, okay, so at time point T1, the output is still high, okay, and Vn has already switched, and Vn is equal to VDD, okay, and then time point T2, Vn of course is VDD because it has switched, and my output has reached the 50% point, so my V out is really at VOL plus VOH over 2. So here the upper one is really VOH, okay? So we start from VOH and we're going to reach, since the final value is VOL, the 50% point is the midpoint between VOH and VOL. So being comfortable with these definitions is very important because you will rely on them to find the value of the current at this point, to find the value of the current at this point, its average value, and then the time for the delay. Okay? In a similar fashion, if the input is switching from high to low, we expect that the output to rise. Okay, so we're going to measure the TP low to high at the output, and this time it is going to be different points. This is my T2, this is my T1. So my T1 is when my input has already gone low, okay, or zero, let us say, and my output is starting from VOL. And then my time point T2 is my input is still low, so Vn is 0, and my output is expected to be rising to the midpoint, which is VOL plus VOH over 2. So these are my 2 time points that I am very much interested in. Okay, great. The delay now will depend really on the pull down strength, or how big the devices are, or how small their effective resistance is, and on the load, on the capacitive load at the output node. So if I am pulling down the output, then R pull down will be responsible for pulling down the capacitor or discharging the capacitor, and it will be responsible for the delay. Okay. So let us now switch to the see how we can find those values. So this is the definition. TP low to high is for VO rising from VOL to half VOL plus VOH, and then the TP high to low is the time or the V out to fall from VOH to half VOL plus VOH. Okay, so sorry, the clear button is not working for me. Okay, so what we have here is then the average propagation delay. It's half TP high to low plus TP low to high, and the maximum switching frequency is estimated as 1 over 2 TP. This is more like a rule of thumb in the technology, so it assumes that I'm only reaching 50%, but it is not very straightforward, so we don't really worry about it. Okay. طب هلا propagation delay calculation. Great. For the propagation delay, I know my C. I have to know my effective resistance. The resistor-based inverter, one branch is very easy, but the other, or one type of the delay, particularly the TP low to high, is simple for me because when the output is rising, this corresponds for the input to be dropping to 0. And since my input is dropping to 0, this means that the NMOS transistor turns off, and really the device that is responsible for charging the capacitor is the R. Okay, so my switch is off. Okay, my switch has turned off. And since my switch has turned off, then the resistor is fully responsible for pulling up the capacitor. So, okay, I have an RC circuit. It is simple. I can find the RC time constant. This is a single time constant circuit. We know that in this case, V out is going to be equal to V final plus V init minus V final times e to the minus t over tau. This is V final here, okay? And now for this circuit, I know what my V init is. In the RC circuit, my V init is VOL. My V final is going to be equal to VDD. So I can write the equation for my output as V out of T is equal to VDD plus VOL minus VDD times e to the minus t over tau is really RC. Okay, so this is how the output, the equation that the output is going to follow. And accordingly, since this is the equation that the output is going to follow, I can now solve for the time it takes for the output to reach its 50% point. So I'm going to say, well, my output signal is going to look something like this. I know that at time point T1, my output is at VOL, or let us set this as 0 reference so that we don't have to make a time shift. And then at the 50% delay, which is my TP low to high in this case, and هي is 0, يعني TP low to high is only the second point since my starting point is 0, I would have reached VOL plus VOH over 2. Okay, so my objective therefore is to solve for this time at which the output can reach VOL plus VOH over 2. Therefore, I will plug into this equation V out desired is VOL plus VOH over 2, and it is equal to V final plus V init, which is VOL minus VDD times e to the minus t over RC. And it is this t which I am trying to solve for. Okay, it is this t which I am trying to solve for. Okay, do you all remember this equation? Do you have any questions about it? طيب, let us هلا move through the slides. فإذا I have a single time constant. I have a single time constant circuit, and I can use its equation to solve for the time at which my output is going to reach the midpoint. Okay, this single time constant equation is characterized by as follows. When t is 0, I will have my V out equal VOL. ليش؟ لأنه e to the 0 is 1, and this will be VDD plus VOL minus VDD. It's VOL, which is V init. Okay, and when t tends to infinity, e to the minus t over RC is going to tend to 0, and therefore V out will be equal to VDD, which is V final. Okay, so this is the equation of the single time constant. And now what we are really doing, we are saying since at t0 it starts at VOL, I want to find the t at which it reaches half or 50% value, so I can solve for t from this equation. Okay, let us now move on. So the output is going to charge, and my objective is to find this point at which we reach half value. Okay, and we're going to see now, since this is a single time constant, V is V final plus V initial minus V final times e to the minus t over tau. The output voltage for me, V final is VOH and V initial is VOL. And for this specific circuit, VOH is VDD. Okay, we reach the 50% point when V out is VOH plus VOL over 2. Okay, and we solve for these values. We end up finding that the time is really RC times ln 2, okay, which is 0.7 RC more or less, or 0.69 RC. Okay, so this is simple because I had a simple RC circuit. Any questions? So now let us look at the general propagation delay calculations. لأنه not always I have RC. Sometimes the device itself is really pulling down the capacitor. So what am I going to do here? So the capacitor current is CdV by dt. Okay, and if I want to really find the time needed, then I'm going to flip this here. So I'm going to say that dt equals C dV over I. Okay, and therefore the delay is going to be the integral, okay, of this quantity here. Okay, this is a little bit complex. We're going to simplify it. We're going to say that since I cannot get at every time point because the equations of the transistor are nonlinear, the current, I'm going to approximate Tp or the delay as C, yani delta T, as C times delta V integral of dV over the interval over I average. Yani I'm going to assume that the current is an average quantity. So this will be C over I average. Since it is average, it's a constant, I take it out. And then the integral of dV will be C over I average times delta V. Then delta V, I know what it is. It is the delta from time 0 to time Tp low to high. And the I average, I have to calculate it as the average during that interval. Great. So this is called the average current method, and we use this equation to calculate the delay. So we're going to start with the resistor pulling up the capacitor just because the I average is simple to demonstrate, and then we will move on to the case of the transistors. So for the same example, where the resistor is charging the capacitor, we're assuming that VO is at VOL at T0, and at TP low to high that VO is half VOL plus VOH. Okay, so it is moving, the capacitor voltage is moving from this point to this point. So we will say that at time 0, VO out is VOL, and therefore I1 is really VDD minus VOL over R. Okay, and then we will say at time TP low to high, or the 50% delay, and at this time point, my V out was VOL plus VOH will be over 2, and therefore the second current value which I'm interested is really VDD minus VOH plus VOL over 2 over R. Okay, and then we're going to say therefore that my I average is equal to I1 plus I2 over 2. So this is the first quantity. The second quantity that I'm interested in is the delta V, which is the voltage change over this interval. So the delta V is really V2 minus V1, which is VOL plus VOH over 2 minus VOL. Okay, this is my delta V. So this is my second quantity. Now I can calculate the delay as C times delta V over I average, and we will see the detailed equation. Anybody has any question about the average current method? Okay, let's see what the slides say. So we're saying that I average Tp equals C delta V. The current at the first time point is equal to VDD minus VOL over R, which is VOH minus VOL over R, if we want to interpret it that way. And then at the second time point, which is here, the current is really this time equal to VDD minus the value of V out at the 50% point over R. Okay, and from this quantity, I can calculate really the average currently half of the value of the sum, and therefore I can find my delay to be C times delta V at these 2 points. Okay, minus يعني هي this minus this over I average. Okay, if we do the calculations, okay, we will wind up finding that this is the delta V basically. We will end up finding that the delay comes out to be 0.67 RC because the VOH and VOL, the results are function of VOH minus VOL. So if you notice here, this is VOH minus VOL and delta V is function of VOH minus VOL times time constant. And so I wind up only with the RC term in this example. And this is very close to the exact value, which is 0.69 RC. Okay, so we're showing that for the single time constant, it is a good approximation. Therefore, we're going to proceed with this and we are going to use it in the context of the transistors. Anybody has any question about this method? Okay, so let us now then move forward. First, we're going to talk about the CMOS inverter. And then we are going, in the context of the CMOS inverter, use the average current method to solve for the Tp low to high and Tp high to low. We avoided using it for the resistor-based inverter for the pull down because we assume that we have to neglect the presence of the pull-up resistor and بصير في عندنا 2 devices to reach VOL. In the context of the CMOS, one of the transistors will be on and will be pulling the capacitor to VDD or ground. And what is CMOS? CMOS is complementary, pardon me. CMOS is complementary MOSFET logic, okay? Complementary means I will have a pull-up network and a pull-down network, okay? And the pull-up network, either the pull-up network is on and it pulls the output to VDD, or the pull-down network is on and it pulls down the output to ground. But the two, if this is on, this will be off, and vice versa. The two cannot operate together at the same time. Well, during transition, yes, but really one is turning on, one is turning off, and one will be stronger than the other, and it will pull the output to its side. Okay, so the CMOS is adopted because of its simplicity. As we will show later, it will have zero static power dissipation, and the noise margins are close to ideal, so we can design it to switch around VDD over 2. We don't have to worry about the size of the resistor. So the simplest CMOS gate is really the CMOS inverter. The CMOS inverter, it has a PMOS device, okay, and an NMOS device, and they are both connected to the input VN, okay? And now this is my output here. Now, one rule of thumb about the PMOS is really active low. كيف يعني active low؟ يعني when the input is 0, the PMOS will turn on and it will turn off otherwise, and then the NMOS is active high. Okay, so the NMOS is active high. It requires the input to be high to turn on. We can view the two transistors as some small resistance and a switch, a P switch and an N switch, and they work opposite to each other. When the N closes, the P will open and vice versa, because when the input is 0, okay, the P will be on and the N will be off, and vice versa. Okay, now this value of the resistor, if you recall when we talked about the voltage transfer characteristic, we said that in the resistor-based inverter that the NMOS is in the linear region when V out becomes low, because if V out is small, the VDS is small. Here I have Vn, so Vn is high. So Vn is high and the output is small, VDS is small. So the NMOS, when it pulls down in the linear region, and we will study these cases in detail later. In a similar fashion, the PMOS, when it pulls up, it will be in the linear region. We'll prove it later. But let us look now what is the resistance of the NMOS device in the linear region. So for the NMOS to pull down, okay, output to low, it will be in the linear region. This we'll prove it later. The current I is equal to half K times 2 times VGS minus VT times VDS minus VDS squared. Now, if somebody tells me that VDS is very small, much smaller than VDD in the output low, okay, I can ignore this term. لأن مثلا إذا عندي 0.1 VDS squared هتصير very small. Okay, so I can ignore it. This and this will cancel, so the current will be equal to K times VGS minus VT times VDS. Okay, now if somebody asks me to approximate the resistance IDS when the NMOS is in linear region, when it is pulling down the output to low, I am going to tell them that I can approximate it as V out, which is VDS, okay, over the current, right? So it is the V, voltage over the current, and the current is K into VGS minus VT times VDS. So I can tell them that the resistor is approximately 1 into K over K into VGS minus VT, and VGS for the NMOS, and we will talk about it also in detail later, is Vn. Okay, therefore, according to this, you will see on this slide that the resistance for this pull-down switch can be approximated by 1 over K into VDD minus VT. Then when Vn equals VDD, this will be off, this will be on, and it will be linear, and the output will be very low. And we will explain them later. But I'm just saying this to tell you where this equation came from. And in a similar fashion, there is a resistance for the PMOS when the switch is on. We can approximately use this resistor value. But let us now dig into the details slowly. Okay, so let us see what happens to this switch. So for this inverter, when Vn is less than Vtn, when Vn is 0, for example, okay, the NMOS will be off, so the switch will be open, and the current that is flowing here will be equal to 0. Okay, so the current that is flowing here will be equal to 0. Okay, and we expect that the PMOS is going to pull up the output all the way to VDD. مجرد ما الكرنت يصير equal 0 in the branch اللي هو between VDD and ground, one of the devices is going to pull the on device, which is PMOS in this case, will pull the output to its side. Okay, so let us see how we derive this scenario. Okay, let us see how we're gonna derive the scenario, and let us analyze, let us analyze the, and let us analyze this relation. Okay, so let us look here. I have the PMOS in transistor, and I have the NMOS. Let me draw it in a different color. And I have the NMOS transistor. Okay, and they are both trying to connect to the output, and then the same VN is really connected to the two. Okay, this is connected to VDD in this side, and then the output is really between the two of them. So the first thing that we need to be comfortable with is to really know how to label the nodes. This is the source near the arrow for the PMOS. This is the gate for the PMOS. This is the drain for the PMOS. And then for the NMOS, this is the source near the arrow. This is the drain. And this is the gate. And so we are going to build a table for the NMOS. Okay. And we're going to build another table for the PMOS. For the NMOS, we are going to find what VGS minus VT is, what VDS is, and we are going to find the region. Okay. And in a similar fashion, for the PMOS, we are going to solve for the quantities VSG minus magnitude of VTP, VSD لأنه عم ناخدهم بالabsolute value عم نقلبهم هو بضلهم positive, and we are also going to look for the region of operation. Okay? هلا, in this problem, I am saying that given Vn equals to 0. طيب, let us see what is بالنسبة للNMOS transistor. Vn is really Vn. VGS is equal to Vn. So this is Vn minus Vt. And VDS is equal to V out. هلا, in this scenario, because the input is 0, this means that VGS is equal to 0. So the device will be off. And therefore In will be equal to 0. Okay? طب, for the PMOS side, let us look at the PMOS side. What is VSG? And this is VDD. VSG is equal to VDD minus Vn. Okay? And this is really, since Vn is equal to 0, it's equal to VDD minus 0. So VSG is greater than VTP. Therefore, the device will be on, and I can continue to calculate VDD minus 0 minus VTP is VSG minus VTP. Okay, the device is on because VSG for the PMOS is equal to VDD and it's greater than absolute value of VTP. Okay, so I continue to plug into this table and I find that VSG minus VTP is VDD minus 0 minus VTP. Now, when the input is 0, I am solving for VOH. When the input is 0, I am solving for VOH. So what is VSD? VSD is really VDD minus V out. So for the PMOS, VSD is VDD minus V out, which is VOH. Okay, now those two quantities. On one side, I have VDD minus VTP. Let us say that VDD is really, let us say that VDD is around 2.5 volt. So let us say that this is 2.5 minus 0.5. And on another side, I have VDD minus VOH, which is very close to VDD. Which is smaller? Which quantity is smaller? What region I am in? So I have my PMOS transistor And I have here 2.5 minus 0.5. Let us assume that VOH reaches 2.4 volts. So this is 2.5 minus 2.4, which is approximately 0.1. Therefore, this quantity is smaller. When VDS is small, when VSD is small, I would be operating in the linear region. Okay, I would be operating in the linear region. So IP will be IP linear, and now I can solve for what is really VOH. Okay, so to solve for VOH, what we typically do is we really say that IN equal IP by KCL, but IN is equal to 0, and IP is really half K times 2 times VSG minus VTP is VDD minus VTP. Okay, and VSD is VDD minus VOH. Okay, minus VSD square, it's VDD minus VOH squared. Okay, so this is the current. My current is of the form of half K times 2 times VDD minus magnitude of VTP times X minus X squared, and this quantity is 0. What would make this 0? So I have A times X. Okay, I have some A times X minus B times X squared equal to 0 if and only if X equals to 0. So what is going to really affect my result, okay, is that solving or the root for this solution will be X equal to 0. Therefore, what can make the current at IP equal to 0 is really having the term VDD minus VOH equals to 0. So having the term VDD minus VOH equal to 0 can set this equation to 0, and therefore the solution will be when if and only if VDD minus VOH equals to 0, if and only if VOH equals to VDD. فإذا two things we take with us from this is that the VOH should be equal to VDD and the PMOS is in the linear. Sorry.